Swayam Prabha. Digital India. Educated India.
Welcome back, student, to this fourth lecture of the pipe flow. Last time we saw the Darcy friction factor, and we saw that for the fully developed laminar flow the Darcy friction was 64 by Re, whereas in terms of wall shear stress it was 8 tau W by rho V square. Okay, now we are going to see about the energy in a fully developed laminar flow. So, consider the flow between two locations, alright, and if we consider flow between two locations, we can write Bernoulli's equation. So, the pressure head, the velocity head and the datum head is equal plus the energy loss on the other side if there is an energy loss in terms of head loss HL. This alpha and alpha 2 we take 1 for the uniform velocity profile, and alpha is greater than 1 for non-uniform velocity profile. We are assuming alpha is equal to 1 because our velocity profile is uniform. So, for fully developed flow alpha 1 is equal to alpha 2 is equal to 1, and here the head loss accounts for energy loss associated with the flow, that I have told you before. So, we have written Bernoulli's equation at between point 1 and point 2 accounting for the head loss or the energy loss, alright, and this is due to the viscous dissipation. For in viscous flow there will be no head loss, HL is going to be 0, alright. So, with this background we will rewrite equation number 13. Okay. So, we will get P1 by gamma plus Z1 minus P2 by gamma plus Z2 is equal to HL for uniform velocity profiles, alright. So, what we are going to get P1 minus P2 by gamma is equal to delta P by, because this is if we do P. So, here is P1 by gamma minus, so we can write P1 minus P2 by gamma and this becomes delta P by gamma. Z2 minus Z1 we can always write L sin theta, right, the datum if the slope of the bed is theta, and if we put that here we are going to get delta P by L minus L sin theta is equal to head loss, or delta P minus gamma L sin theta by gamma is head loss, alright, with this simple manipulation, alright. Now, if we use equation 5, you remember what the equation 5 was? Then, so P minus gamma L sin theta using equation number 5 can be written as 2 tau L by R. This will be the head loss, alright. And then head loss can be simply written as 2 tau L by gamma R. This is equation number 15. Now, if we use equation number 2, 2 was using the wall shear stress, and using equation number 2 if we substitute tau in terms of wall shear stress and R, we will see we will get head loss as 4 L tau W by gamma D. So, this is a quick formula for obtaining the head loss in terms of wall shear stress, length of the pipe and diameter of the pipe. Right. So, you should remember this one, alright. And this is equation number 16. It's just a matter of substituting one equation into the other and obtaining what we require. So the beauty of this equation is that 4L tau W by gamma d depends only on the wall shear stress. Now we have written head loss as 4L into tau W by gamma d. All right. This is equation number 16, and this equation is valid both for laminar and turbulent flow. So we have not yet used any approximation specific for only laminar flow. This particular equation, because the substitution that we have done, we have taken tau W and tau relationship that was valid for both laminar and turbulent flow. Okay. So with this we conclude this energy in fully developed laminar flow, and the also this one, since is valid for turbulent flow and so energy also in the turbulent flow. Now we proceed to a broader topic called turbulent flow. Much of it we have already seen in a chapter called laminar and turbulent flow, but for specifically for pipe flow we will go through it once again. The one that we have said was for a general case of flows in the week number 3 that we went. Okay, so here there is a figure that shows time on this axis and velocity on this axis. You see, as the velocity is increasing, until some point the velocity is less, so this is the laminar region. All right. The idea is, if you keep on increasing the velocity, the Reynolds number will increase and the flow will become from laminar to transitional to turbulent. So as you keep on increasing the velocity, until this point it is still transitional until Reynolds number of 4000. Okay, and after that it becomes fully turbulent. So in turbulent flow, the axial component of velocity fluctuates randomly. The components perpendicular to the flow axis appear right, you see here. In turbulent flow, heat and mass transfer are enhanced. That is another important feature that we know. In many cases, reasonable results on turbulent flow can be obtained using the Bernoulli's equation. Many cases, okay, because by putting a Reynolds number as infinity. So talking about the fluctuation in turbulent flow, all parameters fluctuate in turbulent flow, whether it is velocity, pressure, shear stress, temperature, everything fluctuates and they behave chaotically. Chaos is there. Okay. The flow parameters can be described as an average value plus fluctuation. This we have already seen many times, that u can be written as u bar plus u prime, v can be written as v bar plus v prime, w can be written as w bar plus w prime, same with pressure. So this is the average component, things with the bar, and this is the fluctuating component. All right. And these, you see, there is bar and prime. So they can be characterized by turbulent intensity and time scale of fluctuation. Turbulence intensity is nothing but under root of u prime whole square and then average taken over that to the average value. So you see here it is the fluctuation by average value. So you can assume if the fluctuation is too high, the turbulence intensity will be high, because it is fluctuation by average. All right. So in terms of wave averaged or time average, this can be written also like this. All right. So something like this. Correct. So you see we have plotted again it as a function of time, the fluctuations. So here it's not the average velocity, it is the fluctuating velocity component as a function of time. So this line represents the fluctuation, this solid line. The dash 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 represent fluctuation to the whole square, and this line is the thin line here, you see. So this is the fluctuation, all right, the thick line, whereas this line represents u dash whole square, and the average of this quantity is represented by thin line like this one, this one, this one, this one, this one, okay. Now talking about shear stress in turbulent flow. So they represent two sub figures A and B, all right. You see this represents a particle having random velocities here and at a point 2, okay, and this represents the velocity profile, a normal velocity profile, and this represents an average velocity profile. You can see we have plotted the turbulent eddies here, see, all right. So eddies has been represented. So the turbulent flow can be often thought as a series of random 3-dimensional eddy motion ranging from large eddies down to very small eddies. So this is large eddy, and these are small eddies. Vortices, these vortices, they transfer momentum, so the shear force is higher compared with the laminar flow, all right. So in turbulent flow the shear force is much higher than with the when compared with the laminar flow. So the total shear stress in a turbulent flow can be written as combination of two things, shear stress due to laminar and plus shear stress due to turbulence, and this is for the laminar shear stress, and this is turbulent shear stress. We shall go into more detail when we study the modules of viscous fluid flow and computational fluid dynamics about rho u dash v dash. They are called Reynolds shear stress, all right. So therefore the shear stress in a turbulent motion is much larger than the laminar flow. So here, as I said, the shear stress is the sum of laminar portion and a turbulent portion. As shown before, tau is equal to mu du dy minus rho u dash v dash whole bar, all right. So tau laminar plus tau turbulence, where this is fluctuation, and this shear stress turbulence is positive, and therefore it is sum of two shear stresses. Shear stress is larger in turbulent flow. Alternatively, we can also write, so instead of writing we were writing tau is equal to minus rho u dash v dash whole bar, correct, but we can also write tau turbulence as tau turbulence can be written as another viscosity into du dy, and this eta is not equal to mu but much higher, okay, and this is called turbulent eddy viscosity. This is our approximation, all right, where eta is eddy viscosity or turbulent eddy viscosity. So, there was a scientist called Prandtl. He suggested that the turbulent flow is characterized by random transfer over a certain distance Lm, as we have already talked about this in our laminar and turbulent flow module. So, eta can be approximated as rho Lm square into du by dy, where u, this is average velocity. See, you have to appreciate that if we are able to write something in terms of average velocity, it makes our life easier. Okay. And therefore, tau turbulence, if you substitute here, tau turbulence can be written as rho Lm square into du by dy whole square, indicating that tau turbulence is positive. All right. So, this is a figure showing different areas in a pipe flow, which is the layers. So, the area near the wall is called viscous sublayer, then there is something called the turbulent layer, then there is an overlap layer, and then there is an outer layer until the center line. All right. So, you see we have represented tau as a function of r. This is the pipe center line, and you see if this is the total shear stress, at any point you can see the contribution. All right. So, near the pipe, the contribution of laminar flow is very high. All right, but near the, say for example at this point, so laminar is pretty high, but as soon as you move away from the wall, the laminar contribution compared to the turbulent contribution becomes less and less. So, actually we can write that shear stress due to turbulence is at least 100 to 1000 times of shear stress due to laminar. So, laminar contribution is at least 100 to 1000 times less than the shear stress due to turbulence. Now, we said there are several layers in the we have gone into much detail in our laminar and turbulent, but for repetition I would like to go once again very briefly with this and try to solve some problem as well. So, what viscous sublayer? What is viscous sublayer? So, here in this viscous sublayer, which is very near to the wall, the viscous shear stress dominates. Therefore, viscosity is dominant and density is unimportant, as we have seen before as well. Outer layer, here Reynolds stress is dominant and viscosity is unimportant, and therefore density is dominant. So, in the viscous sublayer, we can write u bar by u star is equal to y u star by nu. This is called the law of the wall, where y is equal to r minus small r. U is time average x component and u star is shear stress by rho to the power half, also called as friction velocity. So, there is a curve figure here, all right. And using this figure, this is u bar by center line velocity and r by r is given with different this laminar flow curve is given here, and there is n is equal to 8, n is equal to 6. What that n is, we will come. So, very valid, this viscous sublayer is valid very near the smooth wall. So, this is valid. So, this law of the wall is valid, which is very near to the wall, the value of which is given by y u star by nu less than 5. So, the thickness of the laminar sublayer can be written as 5 nu by u star. This is important to remember. I think you must remember this value. In the overlap layer, you see the overlap layer, you remember this overlap layer, this layer, this log law is valid by u bar by u star is equal to 2.5 ln y u star by nu plus 5.0. I think we have gone through it in our other lecture. Here the coefficients of 2.5 and 5.0 have been obtained experimentally. In the turbulent layer, we can also write it in form of center line velocity, the graph of which was given here. All right. Vc minus u bar, this is called velocity defect law in outer layer, is given as 2.5 ln r by y, or u bar by Vc is equal to, this was the equation for which the curve was given. What is going to be the value of n can be determined from this graph with the corresponding values of r by u by Vc and r by r. All right. So, and this equation is called power law velocity profile, and this n is a function of Reynolds number. All right. So, velocity defect or retardation of flow due to wall effects. Okay. So, this is the curve where using which n can be determined. All right. And if you determine n from this graph, then for corresponding n you can use this table for finding this graph for finding the relationship between u by Vc and r by r. So, in our question probably we will be using this thing, this particular concept. All right. So, I mean this is again a repetition because we have gone through with this in the turbulent layer, but the problem that we are going to solve is completely new and will give you much more idea how to solve for this in the pipe flow. So, the class question is that water at 20 degree centigrade, the nu and rho is given, flows through a horizontal pipe of 0.1 meter diameter with a flow rate of 4 into 10 to the power minus 2 meter cube per second and a pressure gradient of 2.59 kilopascal per meter. If we assume 1 meter pipe length, determine the approximate thickness of viscous sublayer, formula we know, determine the approximate center line velocity Vc, and determine the ratio of turbulent to laminar shear stress at a point midway between the center line and the pipe wall. All right. See, if we the thickness of viscous sublayer, we will also find the center line velocity, and for finding center line velocity you see we had this curves here. We can find n here first and then using n we can find the center line velocity, and the best part is that we will be able to appreciate by finding out the ratio of the turbulent to laminar shear stress at some point. Okay. So, we will solve this question in this lecture and we will finish this particular lecture after the solution. Okay. So, thickness of viscous sublayer is going to be delta S u star by nu is equal to 5. So, delta S 5 nu by u star. All right. So, we do not know u star, but u star can be written as tau w by rho to the power half. Okay. And how do we obtain the wall shear stress tau w? So, tau w can be obtained from pressure drop formula of delta P is equal to, you remember 4L tau W by D that we derived. It is valid because it is valid for both laminar and turbulent flow. All right. So tau W would be d delta P by 4L, and after substituting the value we are going to get 64.75 or 64.8 Newton per meter square. Therefore we can get U star as 0.255 meters per second, and therefore we can get thickness of viscous sublayer as 5 into nu was 1.004 into 10 to the power minus 6 divided by 0.255, and that gives us 1.97 into 10 to the power minus 5 meter, or delta S is 0.02 millimeters. So you see how thin this viscous sublayer is. Now second, we have to obtain the center line velocity. So we know that the center line velocity can be obtained from the average velocity using that power law velocity profile. Okay. So first of all we find average velocity as V is equal to Q by A. Q was 0.04 pi by 4 into 0.1 square. So velocity we are getting 5.09 meters per second. Corresponding Reynolds number will be Vd by nu. Alright, values we already know. V is 5.09, diameter is 0.1, and it is 1.044 into 10 to the power minus 6. So it comes to be 5.07 into 10 to the power 5. Okay. So with this Reynolds number, using Reynolds number of this 5 into 10 to the power 5 corresponds to the value of n is equal to 8.4 from the curve. All right, this is important to note it down. So we look at Reynolds number and we look at the curve. All right. All right. So we can use this formula, U bar by Vc is equal to 1 minus R by R, the center line velocity formula, divided by 1.84. Okay. And we also know that Q is equal to A into V, or integral U dA. All right. So we use U bar from here. All right. So Vc will come out, and R is equal to 0 to R is equal to capital R, 1 minus R by R to the power 1 minus R, and integral 2 pi R dr. We integrate. Okay, and after integration we will see, we will get 2 pi R square Vc into n square divided by n plus 1 into 2n plus 1. Now we substitute n is equal to 8.4, and this Q is also equal to 2 pi R square, sorry Q is not 2 pi R square, this will be pi R square into the velocity that we had obtained last time. All right, that was 5.09, the average velocity. Okay, because this is also equal to Q. So now if we equate both of those, what we are going to get, V by Vc is equal to 2n square divided by n plus 1 into 2n plus 1, and we substitute the value here. All right. Therefore, Vc will be 1.186 V, and V already we know 5.09. So, Vc is going to be 6.04 meters per second. So, that is part B. All right. If you remember, for laminar flow, this Vc was 2 times the average velocity, but in turbulent flow Vc is not 2 times, because V was 5.09 and Vc is not even 1.2 times also Vc. So, but the center line velocity is lesser than what it should be in the laminar flow. All right. Now, the C part, we know we are calculating shear stress, it is 2 tau W R by D. All right. So, tau is 2 into tau W we have already calculated as 64.8, R is we have been given, we have to find this distance R, at what distance small r is given. So, this is coming out to be tau is 32.4 Newton per meter square. All right, and this is sum of both laminar plus turbulent. We also know that tau laminar is given as minus mu du bar dr from the velocity profile law. All right, and then from the velocity profile law, if we try to find out du by dr, it is going to be minus Vc by nr into 1 minus r by r. All right. Velocity profile we can write. All right. So, we will calculate du dr. So, minus, it is all we already calculated, and n was we already found out from the curve 0.05 into 1 minus 0.025 already given, radius was 0.05 into 1 minus 8.4 divided by 8.4. So, du by dr is coming to be minus 26.5 per second. All right. Therefore, tau laminar will be minus mu du dr, and that comes out to be minus mu is 1.004 into 10 to the power minus 6 into 26.5. So, tau laminar is coming out to be 0.0266 Newton per meter square. So, ratio of tau turb to tau laminar will be tau minus tau laminar divided by tau laminar. All right. So, 32.4 minus 0.0266 divided by 0.0266, and this ratio comes out to be 1217 almost. So, you see the ratio of the turbulent shear stress to laminar shear stress is of the order of thousands, as we have claimed before. All right. So, I think this is a fine place to stop this lecture, and we will continue with our further topics in our next class. Thank you so much for listening.